Our next company is Osazda Energy from Albuquerque, New Mexico.
I'm April Jeffries, Director of Business Development from Osazda Energy. And today I'm here to talk to you about the promise of solar energy, a challenge it faces, and how we are trying to solve that challenge. By 2035, billions of solar panels will be installed to decarbonize the US electric sector to help mitigate the worst effects of climate change. Solar photovoltaic technology is something I get very excited about, but is a little bit boring to look at. There are no moving parts. But solar panels supply clean, modular, easily deployable, scalable energy that has the potential to operate without maintenance indefinitely. However, there's a problem. Solar cell cracking is one of the top 3 causes of field failures. Now, I'll let our chief engineer, Andre Chavez, and our CTO, Dr. Han, tell you a little bit more about that in this video.
Designed for decades of outdoor deployment, solar panels are exposed to harsh environmental stressors, including wind, hail, extreme high and low temperatures, and heavy snow loads. Unfortunately, solar cells, the power-generated components of the solar panel, are necessarily thin and fragile and frequently crack in the field. These cracks are usually too small to be seen by the eye, but can severely decrease the amount of power produced by the solar cells.
What we're trying to do, much the same way when you build concrete buildings, you use steel rebar to make the concrete stronger. We're doing conceptually the same thing. We're putting carbon nanotubes into the silver paste to make them stronger, so they become crack tolerant, stretchy, and when the silver metal lines actually break, these exposed carbon nanotubes tend to bridge the gap electrically, and also they tend to self-heal when the gap gets close together or get gaps closed and connecting the 2 metal lines.
So, the problem of solar cell cracking is ubiquitous. Solar cell cracks are everywhere, but understanding the magnitude of the problem is a little bit challenging. This requires large-scale, costly electroluminescence studies. So what we did to better understand how big of a problem this was is we collected literature, case studies, and spoke to experts in the field. And what we found from our case study and literature review is that there is no trend in how bad solar cell cracks are for power performance degradation. Sometimes they're catastrophic and sometimes they're just minor losses. So we spoke to an expert in the field that does aerial infrared imaging of operating PV power plants. And they also determined the root cause of the underperformance. To date, they've done over 39 gigawatts of aerial infrared imaging. So probably one of the best people in the world to talk to about this. And what we found was that for sites that are operating normally, just normal wear and tear, about 0.2 to 0.5% power underperformance is attributed to solar cell cracking. In a more problematic site, that can be around 1 to 2%. And for sites that have gone through hail damage or poor installation practices where someone might have stepped on the panels, that can lead up to about 20% of power underperformance from cell cracking. In terms of dollars, just from the normal wear and tear case, solar cell cracking decreases power output and costs hundreds of millions in solar energy losses annually. Over the next 5 years, just for the normal wear and tear case, that will result in over $5 billion in losses. As we continue to deploy more and more solar panels to combat climate change, the climate is already changing, and in turn creating even more severe and more frequent convective storms. And this is causing a challenge for deploying more solar energy. An example of this that's causing a ton of concern in the industry right now is hail damage. A 2019 hailstorm, for example, in Texas, caused $75 million in damages to a single solar farm. And events like these ones are becoming more frequent, and this is causing a hardening of the insurance market. Basically, insurers are no longer offering full coverage for hail damage, and this is causing costly slowdowns in negotiations and development between financiers, developers, and long-term asset owners. This is also causing solar asset owners to seek more durable technologies as they are the ones most financially at risk. As you can imagine, solar panels are used outside of solar power plants, and those environments can be even harsher. Think about takeoff and landing stresses from unmanned aerial vehicles, from space vehicles and satellites, and transportation, installation, and deployment in secluded and remote locations. And that can be deserts overseas to the surface of Mars. Now, for solar cells in space, there's not a lot of publicly available data on how bad this problem is. But what we do know is that solar cells that are used for space applications are roughly 400 times the cost of those that are used for normal solar power plants. So this can be an extremely costly problem for space applications, and solar panels are also often mission critical in these cases. Our solution to the solar cell cracking problem is our MetZilla Additive technology. Osazda Energy engineers a carbon nanotube-based additive for electrode materials. Our additive is incorporated during the standard solar cell manufacturing procedure, and it is a preventative measure. Okay, so our MetZilla additive is incorporated into silver paste or other electrode material. I have silver paste here because that is the most common electrode material for photovoltaics. And our additive makes fragile electrodes tough and elastic, capable of electrically bridging cracks in solar cells, and this results in more solar energy harvested, minimizing energy losses from solar cell cracking. So our envisioned business model is as follows. Our MetZilla additive is incorporated into silver paste or another electrode material. This results in more solar energy harvested, which is value added. And that value added is shared between our direct partners and their downstream customers. So that is more solar energy harvested equals value added. And our customers will also be our partners, and they will be silver paste and solar cell manufacturers. We have a working relationship with DuPont, a silver paste manufacturer, and we've been customizing our additive for use in their product for about the past 2 years. We plan to have 3 different revenue streams: a development service to customize our additive for our partners' products, a licensing royalty, and a formulation refresh for whenever our partners update their product formulation. We need to verify that our additive is still compatible and optimized for that formulation tweak. Okay, so total available market. Here we're looking at the silver paste market, again, because silver paste is the most common electrode material for photovoltaics. In 2019, the total available market was $3.8 billion, and this is projected to be about $5.7 billion in 2026. So I mentioned our potential partners, potential future customers. 2 that we have relationships with already are Heraeus and DuPont, and in 2019, together they made up almost 50% of that market share. Now, when we look at other markets, you can really imagine our additive being used in any type of electrode that could benefit from enhanced electromechanical properties or enhanced durability. So think about things like flexible electronics, bio-integrated devices, and wearable electronics. Oh, wrong way. There we go. So how does our technology compare to our potential partners and to our competitors? Our MetZilla enhanced electrodes have 5 times the fracture toughness. the ability to bridge cracks greater than 60 microns, which is well above the 5 to 20 micron crack width that's commonly seen in the field. We add our additive in such small quantities that it does not negatively impact the electrical performance of the electrode, and it does not significantly increase the cost. And all of this results in increased solar energy harvested. So just to show you a proof of concept, when our team first started working on this, they developed this for use on high-efficiency 3.5 solar cells used for space applications. So what I have here are two electroluminescence images. Essentially, what you're looking at is an electroluminescence image before cracking and after cracking for standard electrodes. On the left, you see a bright orange square that's fairly uniform in brightness. Now, bright means good electrical performance. On the right, after a cell crack is introduced, you see a dark region appear across there, and that is where the crack is electrically isolating that entire dark portion of the cell, meaning that it's useless. Okay, so now here we go. So now let's look at our MetZilla enhanced electrodes. Again, before cell cracking, you see uniform bright region across the entire solar cell, good electrical performance. And then after cracking, you see some disturbances, but you still see electrical conductivity and bright regions across the entirety of the solar cell. Okay, so quick overview of how our technology came about and where we're going. In 2014, the Air Force Research Laboratory reached out to our CTO, Dr. Han. He's here in the audience today. And they reached out with an anticipated problem of cell cracking for their aerospace applications. They began a collaboration at this time. And then in 2017, our CEO, John Chavez, came together with Dr. Han and founded Osazda Energy with company formation funding from the New Mexico Startup Factory. Since then, our team has raised over $3 million in non-dilutive grant funding, largely from the Department of Energy. With this funding, we brought our MetZilla technology to TRL of 4 with lab scale production. We are in progress with mini module and full-size module accelerated stress testing. And at the completion of our DOE grant in 2022, we anticipate achieving a TRL of 6 at the end of that time. So we have a small but mighty team of 8. And a new addition to our team this year is Dr. Homer Antoniadis. He is a strategic advisor for us. He was the former CTO of DuPont Photovoltaic Solutions. And before that, he was the CTO of Innovalite, which was a solar electrode startup that we hope to follow their successful pathway that they sort of followed. So having him on the team is a huge asset. And now, looking forward, we are currently seeking $1.8 million in seed funding to scale up for business development and final validation for market entry. We're also looking for partnerships and just more information on challenges for space PV and other applications. For example, how does electrode durability and cell cracking affect space missions? This is something we do not have a lot of data on right now, so we'd love to talk to you about it. So with that, I would like to say thank you and leave with our ask, which is if you're interested in talking to any of us about the following: seed funding, partnerships, just information on applications or the size of this problem for space. Thank you.